So let's say we had an equation, and that equation was called z equals f of xy. Now this can be any function with two variables of input, and that outputs a single number. And this can be represented, of course, as a 3D graph. And that graph might look something like this. Okay, so this is kind of an arbitrary graph, and we might want to analyze this function, and one way we could do that is we could declare a specific point on this graph. So let's say we had a point P over here, and so we might want to find or kind of isolate the x components of this graph at the point P. And so we might do that by basically trying to find the tracing at a given y value, because we're setting y to be constant. And so that curve might look something like this. And this is kind of a crude drawing. It's basic. Whoops. Let's bring that up. Okay. So that is our tracing with respect to x, and that curve is going to be called curve 1. And so curve 1, in terms of actual notation, can be defined by any given x value, the y-coordinate of P, because again this is intersecting point P, and then any given z value. And that x and z value can be defined by the function. And we could also have another curve with respect to y. And that curve could look something like that, and that's going to be curve 2. And curve 2, much like curve 1, is going to have an x-coordinate defined by point P, and a given y and z coordinate defined by our function. And so we can analyze this even further, because we can, maybe, for example, find the tangents at point P of these given curves. And so let me use a different color here, and we might want to find the tangents. And so let's draw the tangents. That's kind of bad. Let me kind of find the downward slope over here. Yeah, right there. Okay. And so that is tangent number 1, and tangent number 1 and tangent number 2, and curve 2 is kind of straight already, but I'm going to do my best to find its tangent. And so that's tangent number 2. And so the slope of tangent number 2, or sorry, tangent number 1, can be defined by the definition of a derivative. And we learned the definition of a derivative in single variable calc, and so we can use that and define the slope of tangent number 1. And so that's simply going to be the derivative of c1 at the y-coordinates of P. And same goes for the slope of tangent number 2. So let me just, let me bring in a different color. So slope of tangent number 2 could be defined, again, using derivatives. And so we're using curve 2 over here, so the derivative at curve 2 at the x-coordinates of point P. And so this idea of kind of finding the x component or the y component and the derivatives of those components of a given function is defined as the partial derivative. So let me write that down. The partial derivative. And this idea of a partial derivative is actually very much similar to what a normal derivative might look like in functions of single variables. And in that regard, we might have a function, for example, f of ab, and we can define the partial derivative of f with respect to x and with respect to y using notation that is very much similar to what we might have learned at the very beginning of single variable calc. So for example, we might have the partial derivative of f with respect to x at ab, and that's simply going to be, and we're going to use limit notation here. Limit notation is kind of the same, it's the same limit notation that you use in defining a derivative in single variable calc, so we're using the limit as h goes to 0, and we're trying to find the change in the x value, and so we are going to do the limit as h goes to 0 of f of a plus h comma b, and b is going to be constant over here because we just want to analyze the x component of this function, minus f of ab, all of that over h. And so this is going to be this kind of applied in single variable calc. The same applies over here. We're trying to find the change in x over h, and we can do the same thing with respect to y. And so we can do the partial derivative with respect to y of ab, sorry, the partial derivative of f with respect to y, ab, and that's going to be equal to the limits as h goes to 0, and this time we're setting x to be a constant value, b plus h minus f of ab, all of that over h. Now, you might not be familiar with the f sub x notation or f sub y notation. That's because, generally speaking, in terms of technicalities, we might instead use the following notation. This term is called del, and so we're going to say del f del y, or sorry, del f del x, and then del f del y. And this actually might be similar to the one that we use for normal derivatives, which might be df over dx, for example. Whoops, df over dx or df over dy. And I like this del notation much more than actually the normal notation that we use for f sub x or f sub y, because it kind of is much similar to df over dx, but it's a little bit different in terms of the actual notation that we use. I'll kind of be sticking to the original one that we use, though, just for the sake of simplicity. Also, it's kind of faster to write, but it's all up to you. So let me just erase that. Whoops, let me erase that. So that is kind of the idea behind a partial derivative. We're basically trying to find where you're setting a single component of our function to be a constant value, and we're trying to find the change in the other component of our function. And so let's bring in an example of what a partial derivative problem might look like. Alright, so we're asked to find the first partial derivative of the following function, and the following function is f of x, y is equal to x over x plus y squared. Alright, so first thing I kind of notice is that we can rewrite this function to be much more simpler for us, so that we can take the derivative, or the partial derivative, much more easier. So we can kind of remove this fraction over here, and we can instead say that it's x times x plus y to the power of negative 2. And so that makes it much more easier to find the first partial derivative. So first, let's find the partial derivative with respect to x. And immediately, I can see that we can use product rule. So let's say that f of x, f sub x is going to be equal to, and now for product rule, we are first going to find the derivative of this part of the expression, and then the second part of the expression. So the derivative of x is just 1, and so we can just write x plus y to the power of negative 2. And then for the second part of the function, or sorry, the second part of the expression, we can write the derivative of x plus y to the power of negative 2. We can use the power rule, and in order to do that, we just bring down the negative 2, and then we instead change it to negative 3. So bringing down the negative 2, we have negative 2x to the power of, or sorry, x plus y to the power of negative 3. And then we have to use chain rule, and actually, in order to find the derivative of x plus y, treating y as a constant, we can say that the derivative of x plus y is just 1. So we don't have to multiply out anything, because one multiplies by the expression, and we're just left with the expression as is. Therefore, in order to simplify this and make it a much better expression in terms of how it looks, we can say that 1 over x plus y squared minus 2x over x plus y cubed so that is equivalent to the partial derivative. We can simplify this even further, actually, by just saying that x plus y, we kind of remove, or we try to find a common denominator, thus removing the need to have two terms. And then we can simplify this even further by taking out by subtracting x from 2x, or sorry, 2x from x, and so we can say definitively that the partial derivative of f with respect to x is going to be y minus x over x plus y cubed. Alright, so that is only the partial derivative of f with respect to x. We also have to do it with respect to y, and so let me just get more space over here. In order to do that, let's just keep that function up top over there so that we can remind ourselves of it. So what we're going to be doing for that is that first we introduce that notation of f sub y. Now we are treating x's as a constant, so this x remains over here. Now we have to find the derivative of this term because y is contained within it, and so the derivative of x plus y to the power of negative 2 is basically the same thing as what we said originally. We bring down the negative 2, and hence we get negative 2x multiplied by x plus y. Using power rule, we set this power to be equal to negative 3, and the derivative of x plus y, setting x to be a constant, is just going to be 1 yet again, so we're left with the original expression. And so hence we say that the derivative of f with respect to y is going to be equal to x plus y cubed. Alright, that was pretty simple for an expression that looks relatively complicated. Now, let's have another example problem. Alright, this problem asks to find the first partial derivative of the given function, but instead the function, or the expression, is going to be the integral from x to y of cosine e to the power of t dt. Now, we've brought in the fact that there's an integral in the expression, but instead of this being, very complicated, we can actually just use the first fundamental theorem of calculus. And so, in that sense, we can essentially just say that the partial derivative with respect to x is just going to be cosine of e to the power of x, and that's it. That is our partial derivative with respect to x. The partial derivative with respect to y is going to be similar. However, we first need to change the actual premise of the expression by setting this equal to negative the integral from y to x, cosine e to the t dt. Whoops, dt. Alright, so in that respect, we can actually find the partial derivative with respect to y much more easily, because that's just going to be negative cosine e to the power of y, using the fact that if we flip the bottom and top parts of the integral around, then we actually have to negate the function first, and so using that principle we can find the partial derivative with respect to y, and so thus that is our answer. Let's look at one more example problem. Similar to the previous problems, this problem is asking us to find the partial derivative at y at the point 0, 1 for the following function, where f of x, y is equal to y to the power, e to the power of x over y. The key to this problem is understanding that we simply look at x as a constant, and that we have to use product rule, because we have basically two terms containing y over here. So, first we have to derive the first term, which is just going to be y, and the derivative of y is just 1, and so hence we can write e to the x over y. And then for the second term, we can keep the y because of the product rule, and then we also have to derive e to the power of x over y, which is just e to the power of x over y. However, we also have to use chain rule, and so in that respect we can say that deriving x over y, treating x as a constant, we can say that the derivative of that is just going to be negative x over y squared. Canceling out these two y's over here, we can see that the final function is going to be e to the power of x over y minus x times e to the power of x over y over y. And so that is the partial derivative with respect to y. However, we also need to find it at a specific point, that point being 0, 1. And so, just to extend the problem over, we're going to have to basically substitute in the respective values of x and y. So, f sub y at the point 0, 1 is essentially going to be equal to e to the power of 0 over 1, which is basically just 0, minus 0 times e to the power of 0 over 1 over 1. Alright, so this all checks out. E to the power of 0 is basically just 1, and since there's 0 over here already, we can just say that it's 0. And so hence 1 minus 0 is just 1, and so that is the solution to that final problem. I'll be posting this whiteboard under the description of this YouTube video. Thank you so much for watching. If you have any questions, please write it in the comments. And thank you so much for taking the time to watch it.